Section 5.4 is power. We're specifically going to be looking at mechanical power here. The two objectives are to relate energy and time in terms of the power produced or needed, and to determine the power needed to do work in different types of scenarios. Let's start by taking a look at the definition of power. Power is the rate at which energy is transferred, or the rate at which work is done. So let's think back to our example. If a person lifts a barbell over his or her head, and another person lifts the exact same barbell over his or her head, but one lifts faster than the other, then they have different power generated, even though they're doing the same amount of work or exerting the same amount of energy. Remember, the energy is really the change in potential energy from the beginning state to the final state, but the power is that change in energy over a given time period. So power is a rate of change. Just like velocity was a rate of change, it was displacement over time. Now, our first equation for power is just the change in energy over time, which is, again, the rate at which energy is transferred, or the rate at which work is done, which is work over time. Either of these are fine, and again, the units are the same. Energy and work have the same units of joules. So depending on the problem, we may have to use one or the other of these two. Now, if we go ahead and take a quick look and look at this definition, we can see that we can come up with a third equation, actually. Work, if you remember, is defined as FD cosine theta. Now, in these problems, we're going to be looking at power that is performed in the same direction in which the force is applied. So that means that theta has got to be 0 degrees. So this is really just 1. So it drops off. So we're leaving us with power equals force times distance over time. But if you think about it, distance over time is really speed. So this really, in the end, is power equals force times speed. So this is our third equation, power equals force times speed, which can be used, again, if we have the force and speed. Or we could use one of these equations, this one here, or we could use this one here. So we have three choices to use equations for power. The units for power are watts, and a watt is really a joule per second. Again, work is measured in joules, time is measured in seconds, watts are measured in joules per second. You should be familiar with the term watts, having heard like 60-watt light bulbs, 40-watt light bulbs. Those are the power ratings. Now those happen to be electrical power. We're going to be looking at mechanical power in these examples. Alright, example 1. 2 horses pull a cart. Each exerts a force of 250 newtons at a speed of 2 meters per second for a total of 10 minutes. In part A, we're going to calculate the power delivered by the horses, and in part B, we're going to try and determine how much work is done by the 2 horses. So if you and a friend are pulling on a desk together, your forces are combined. It's like they're adding one another. So our total force in this problem is 500 newtons. The speed given in the problem is 2 meters per second, and the time period is 10 minutes. Now, we can't have it in minutes, it needs to be in seconds, so I'm going to write 600 seconds. We have three possible equations we can use for power. Let's write them down and analyze. We have power equals delta energy over time, power equals work over time, and power equals force times speed. At first, it may be tempting to use one of the first two formulas because we have a time period, but we'll notice that we don't have delta E or W. We do, though, have the force applied and the speed in this problem. So let's go ahead and plug these two quantities in and get a power. So the math is pretty simple. Power equals 500 newtons times 2 meters per second, giving us a power rating of 1,000 watts. For part B, we want to know how much work is done. So clearly we're going to use this formula to find the work done. Now to do that, let's take a look. We'll write our equation out, power equals work over time. We'll then solve for work by multiplying by time. So work is equal to power times time. We have the power right here. We have the time right here. If we multiply those numbers together, we're going to have 1,000 watts times 600 seconds, giving a total amount of work of 600,000. And now let's take a look at what the units are going to be here. Our units are going to be joules, and let's prove that. Why are the units going to be joules in this problem? Well, a watt is simply defined as a joule per second, so these seconds end up canceling, leaving us behind with joules. Now you could also write this answer, instead of writing 600,000 joules, you could write 600 kilojoules, remembering that kilo means 1,000. So 600 kilojoules is really 600,000 joules. Example 2 says, how much power is needed to lift an elevator with a mass of 500 kilograms if it travels at a constant rate over a vertical distance of 100 meters in a total time of 15 seconds? So let's start with our givens here. The mass is 500 kilograms. The vertical distance is 100 meters. The time period is 15 seconds. And the velocity is a constant, which is important for this problem here. It's important because since we're moving at a constant velocity, we can remember that we have equilibrium in the vertical direction. So the weight of the elevator is pulling down. So I can think of it this way right now. Here's what's going on. The weight is pulling down, and the cable is pulling back up. Force of tension. Okay, tension in the cable. So when we take a look at this problem in a moment, we're going to have to think about the force applied, and notice that the force of tension is equal and opposite of the gravitational force here because we're in equilibrium. Remember, whenever you're in equilibrium, F net equals 0. So it would be Ft minus Fg equals 0. So Ft, the tension in the cable, or the pull upward, is equal to the weight of the elevator. Now, with that said, we can go ahead and use this formula right here, because this is really Fd cosine theta. Now remember, it's being moved upward and it's being pulled straight upward. So these both vectors are in the same direction. So theta is 0. So this becomes cosine of 0, which is just 1. So it's really Fd over t. But the force is the force of tension in the rope, what's pulling upward. But remember that the force of tension is equal to the weight in this problem because we're in equilibrium because it's constant velocity. Therefore, the weight is mg, so Ft is really just mg. So this becomes mg for the Ft times the distance traveled over the time period. We know all of these quantities, we can plug in m times g times the distance traveled all over the time period. If we go ahead and calculate this, we're going to end up getting 32,700 watts. Now that also could be written as 32.7 kilowatts. So we solved this problem by using work. Now let's solve this problem again. The same exact problem, but by using this formula. Change in energy over time. And what you need to ask yourself is this. What kind of energy is being changed? Clearly in this problem, the velocity is constant. So there's no change in kinetic energy. The kinetic energy in the beginning is equal to the kinetic energy at the end. There's no change in kinetic energy because the velocity is constant. But there is change in potential energy because I'm changing height. I'm moving from lower height to higher height. So since we have vertical motion in this problem, that means that there's a change in the potential energy of the object. So we'll do the same approach, but we'll think about this as the fact that it's really delta E, or the change in potential energy. So the final potential energy minus the initial potential energy over the time period. Well, if you think about it, let's draw an elevator. We'll call this the ground, where the elevator is sitting here, and then it's going to move up to the top level. Well, it says it moves a distance of 100 meters, so we could say that YF is 100 meters. And then that YI is ground level, so 0 meters. So for this problem, when we continue writing our formulas, PEF is really mgyf, PEI is mgyi, all over time. But notice that because yi is 0, this part doesn't matter. So you end up with the exact same formula. This reduces to mgyf over time. Take a look. mgd over time, mgyf over time. They're identical because the distance traveled is 100 and yf also is 100. So even though I used this formula earlier, I could use this formula and then plug in these numbers to get the same answer. Alright, the third example. If a car with a mass of 1,800 kilograms accelerates from a velocity in a straight line of 3 meters per second to 10 meters per second in 15 seconds, then what is the average power delivered by the car's engine? So we're trying to find out how much power the engine delivers. So we can see that that's based on several factors. First, the mass is 1,800 kilograms. The initial velocity or initial speed doesn't matter because it's velocity in a straight line. So velocity and speed will be the same. The final speed and the time period. Since the car is moving in a straight line and it's not moving vertically at all in this problem, there's no potential energy involved. There's no springs in this problem, so there's no spring energy involved either. So the only energy we have is kinetic energy. And we can see that clearly there's a change in velocity, so there will be a change in kinetic energy. So we could start and say that power equals change in energy over time. The energy change is kinetic final minus kinetic initial over time, which is 1/2 mvf squared minus 1/2 mvi squared all over time. We can take that equation and we can factor out the 1/2 m in the front, which ends up yielding 1/2 m parentheses vf squared minus vi squared all over time. So we have our variables. We can plug in for each of them. We have 1/2 times mass times final velocity squared minus initial velocity squared all over the time period. If we go ahead and calculate this, we'll end up with a solution of 5460. So the power generated by this car's engine is 5,460 watts. Now, one thing to point out is that technically we could have, instead of using this formula, we could have used power equals work over time if we remembered that work is defined as the change in kinetic energy if there's no vertical motion. From the work kinetic energy theorem, this is really delta KE, which is indeed what we ended up using anyway. So either of those starting formulas would have worked. Your homework from this section is from page 189, some problems at the top, and then one of the problems at the bottom.